I'm really excited to be here. So thank you so much for joining in and for inviting me. And moving forward, if you're comfortable, please call me April. No one at work calls me Dr. Jewell. It's rare that I hear that from anybody. So if you're comfortable, please call me April. And I wanted to tell you a little bit about some of the work I'm doing at the Jet Propulsion Lab, or JPL. So if you're ready, I can take control. Okay, so what I'm going to talk about today is some work we're doing on ultraviolet detectors for astronomy and astrophysics. And this is all stuff that we're doing at JPL, which is also part of the California Institute of Technology. So JPL, we are in Pasadena, California. We were founded in 1936 as a graduate student project, from a professor at Caltech. He and some of his graduate students were doing some rocket experiments in Pasadena, and the locals got a little nervous. So they sent them a little bit further outside of town into the hills of the San Gabriel Mountains, and that's where we are now. We were transferred to NASA upon its creation in the 50s, and now we are what's called a federally funded research and development center under NASA sponsorship. So the way that works is most NASA employees are civil servants, so they work for the government, but we are considered contractors. NASA has a contract with Caltech, the California Institute of Technology, and Caltech manages JPL to do work for NASA. So it's a nice little triangle relationship. So we have about 5,000 employees. Most of us are employees of Caltech. There are a few NASA employees on campus. And our director is also a vice president at Caltech. And most of the work we do, as I said, is for NASA, about 80%. But there's a small percentage of our work that's done for defense programs, and we also do some industry work, but it all has to be related to NASA's goals. And feel free to interrupt and ask questions if you want. I know some people like to wait till the end, just however you feel comfortable. So we start from broad questions that are asked by NASA, and we use those to build missions and develop technologies. So questions, the simple stuff like, is there life on other planets, and how did the universe form? No big deal. So the work I'm going to talk about today is based on silicon detectors, and most of you, whether you know it or not, are very familiar with silicon detectors. They're the same kind of imaging device that's in your digital camera or your camera phone. And the way it works is you have a light-sensitive layer, which is the silicon. A photon or a light beam comes in, and if there's enough energy, it will liberate an electron from the silicon atoms, creating an electron-hole pair. And if you apply an electric field, you can collect those charge carriers and read out the signal. So you can get an estimate of how much light hit the detector and where, and from that you build your picture. Let me just check if anyone is popping in. It looks like no one is trying to get in, so I'll keep going. So silicon detectors are used in almost every space-based mission. I'm showing a few of my favorite images captured from silicon detectors. The one on the left is the pillars of creation taken with the Hubble Space Telescope. And this is an area of a nebula where there are stars forming, there are planets forming. I think it's just a really beautiful example of the kind of detail you can get from a silicon-based image. And the one on the right is a picture taken with a detector on the Cassini mission. This was a mission to Saturn. And this particular mission is from the moon Enceladus. And you can see there are these, looks like a diffuse jet. I don't know if you can see my mouse, but there are these jets of liquid water spewing out from the surface of the moon. So before we had this picture, we knew that Enceladus was covered with an icy surface, but now we're learning that this icy surface covers a liquid water ocean. And we get a lot of detail just by using pictures from silicon devices.
If I can ask a question, how are they
Yep.
sure that the liquid coming out is water?
They do spectroscopy. They have other tools on the spacecraft, and they can look at infrared signatures or look at emission from those jets and plumes. And also, I should say that Hubble Space Telescope has also looked at the moon and has performed their own spectroscopic measurements and have verified that it's liquid water.
Thank you.
So there's a lot of tools. I have lost my pointer. Okay. So there are some limitations to working with silicon, even though it's the most common imager, and that is in its response to light. Silicon in its normal silicon is only sensitive to visible light. And so here on the right, I'm showing the typical response of a commercial detector called a CCD, which is a silicon imaging detector. And if you just the bare native imager, you see the light collection efficiency is about 50% throughout the visible light range. And you can improve that by putting anti-reflection coatings on, just like you would put on your glasses, for example, to minimize reflection. But you can't improve or change the wavelength response. So you're not going, unless you change something about how the detector is made, we're not going to be able to detect light, say, below 350 nanometers. But that is, that's the ultraviolet range is what I'm going to be talking about. And that's specifically what our group is interested in. And we want to see if we can make, or we are working to make sure that we can improve or change the response of these silicon devices. The reason that silicon doesn't work in the ultraviolet is because the photons doesn't penetrate deep enough into the silicon. So here I'm showing a plot with the, we have the wavelength on the x-axis, and on the y-axis we're looking at the absorption depth of a photon in silicon. So you see in the ultraviolet range, which is about 100 to 350 nanometers, the absorption depth is only a few nanometers, and it's not until you get to about 350 and beyond that the absorption depth is more than just a few nanometers and sometimes a few microns. So you have to have a longer wavelength photon, talking about blue or red photons. They will penetrate deeper than an ultraviolet photon. And on the right, I'm showing a band structure diagram. And don't worry too much about the band structure per se, but what we're looking at is energy level differences between the silicon material and an oxide, which forms naturally on the silicon device. And there are energy level differences between those two materials, and that gives rise to a potential well. So it's just a potential energy well. So when an ultraviolet photon comes in, for example, it only penetrates a few nanometers, and it gets stuck in this potential well. It can't get out because there's a huge potential barrier that it has to get over in order to go into the bulk of the silicon material and be detected. So what we call this potential well the dead layer of the detector. And that dead layer is very near the surface. And I'm also showing that there are traps at the surface, because silicon, we're dealing with silicon crystals, and at the surface of the silicon, it's not always a perfect crystal. So there are defects in that crystal layer, which leads to traps where, again, those electrons can be lost. Here, what I'm showing is that if the more defects there are on that crystal surface, the deeper that dead layer gets. So if we want to change or improve the detector's UV response, we have to eliminate this dead layer. And we can do that by controlling how the silicon crystal is grown, which can be a hard problem because we want to either minimize defects or change the band structure or change those energy levels at the surface so that we can collect those electrons. So what we do is a process called doping. So this is where we add a little bit, or in some cases a lot, of an element other than silicon to the device. And we add enough of that very, very close to the surface, enough of that other element that it changes the way the band looks at the surface. So now a UV photon comes in, and if it can get past this very, very thin dead layer, which is now only about a nanometer, then we can collect it. And in our case, the doping element we're using is boron. So it's in group 3 instead of silicon, it's in group 4. And what that allows us to do is change the way the silicon detector responds. So now we see these purple data points are all measured from one of our doped devices. And we see that we have strong response even into the UV and even into X-rays, which are wavelengths below 100 nanometers. So this is one of the only technologies that allows you to do UV detection or UV imaging with a silicon detector. And you may ask how we do it. We start with a device that's already made. So we're not making the silicon detectors, we're just changing them. And that means we can work with the best detectors available. So industry has put a lot of money into silicon devices, so we can take advantage of all of the work the industry's already put into it. We'll remove the very top layer of the silicon with chemical etching and polishing, and then we deposit our own highly doped layer. And that's what I was showing on the previous pages. And we do that with a process called molecular beam epitaxy. It's just a fancy way of saying we heat up. We're working in an ultra-high vacuum chamber, which I have a glamour shot of my machine here on the right. So that's a huge metal vacuum chamber, and the pressure in there is 10 to the minus 10 torr. So there's nothing in there other than what we want. And we have a silicon source and we have a boron source. And we use those, we heat them up so hot that they are actually evaporating single atoms. And those will hit the surface of the detector that we're working with. And they will arrange themselves and grow as a perfect single crystal. The silicon growth rate is very, very slow. It's less than an angstrom per second. And when we're done, we have a very thin layer that we've added, less than 5 nanometers, but the dopant density within that layer is 2 times 10 to the 14 atoms per centimeter squared. And if you look at the silicon surface density, that's about 7 times 10 to the 15 atoms per centimeter squared. So by just adding a few percent of this dopant atom, we can completely change the way the device behaves. And this is all deposited in a single atomically thin sheet. So that's a real advantage of using this ultra-high vacuum deposition technique. So we have a lot of control over the nanometer scale properties of the material that we're growing. I just want to talk about one mission that is using our detectors, and this is called the Star Planet Activity Research CubeSat. And we love our acronyms at NASA, and this acronym is SPARCS. It's led by a scientist, Professor Evgenia Shkolnik. She's at the Arizona State University. And what we want to do with SPARCS is look at M dwarf or red dwarf stars in our galaxy, because we know that the red dwarf stars in our galaxy host billions of planets. So almost every star you see in our galaxy hosts a planet, and some of those planets are in what we call the habitable zone, meaning they are close enough to the sun that they could support life, and not so far away that they're too cold, and not so close that they're too hot. But the UV, the ultraviolet emission from these stars, we know that it is strong and it changes quite a bit. So just like our sun has, we've heard of solar flares, it's flaring fairly often. We know that these red dwarf stars are flaring all the time as well, but their flares are often in the ultraviolet, and that can effectively sterilize a planet that's nearby. So if you have a very strong ultraviolet flare and a planet is nearby, you could potentially wipe out any potential life there. So we want to study the flare activity of these types of stars. So then later another mission may come along and want to study the planet near one of these stars, but if they know ahead of time that the star is flaring and wiping out the potential for life, then they maybe won't spend too much time looking for signs of life there. And we're going to do that with a very, very small spacecraft, to be honest. It's what's called a CUBESAT, and it's called a the size of it is it's a 6U CubeSat. So a 1U CubeSat is 10 by 10 by 10 centimeters. So SPARCS CubeSat is 10 by 20 by 30. And I don't know if you guys can see me, but it's about the size of this box. The whole spacecraft is about this size. That doesn't include the solar arrays that will let us power the mission. And it includes a small telescope. It's about a 9-centimeter telescope, so that's about the size of this cup. And then our camera with the detectors will be sitting behind this telescope collecting the light that will get our science data. And my team at JPL is going to deliver the detectors and the camera for that. And I also work primarily on the detector, but they've also put me in a managerial type role. So I manage the camera work at JPL, which really means I'm looking at budgets and schedules and doing the reporting for our team. So that's the less exciting part of our work. I did want to mention that CubeSats are really kind of changing the way NASA is operating, because normally when you think about NASA, you think about these huge telescopes or spacecraft like the size of a couch, or something even larger. But CubeSats can be really, really small. So if you want to have an idea of what 10 centimeters looks like, it's about the size of this coaster. So talk about the smallest unit CubeSat would be something, if you made a box of coasters. And they're pretty cheap to launch. So there are even some high school that have flown CubeSats. And so I'm showing this website, and I can forward it to Mr. Sanders, talking about the CubeSat launch initiative and some of the work that has been done by middle school and high school students to launch these CubeSats. So with that, I wanted to stop. I know I kind of threw a lot of information at you, but really we're trying to get different kinds of astronomy and astrophysics information with a new ultraviolet detector technology. And so that's what our group at JPL is really passionate about. That's all. And I'm happy to take as many questions as you have.
I have a quick question. Well, hi, my name is Emily Creek, and I'm a junior at GPS. And I just wanted to ask you, you mentioned in your machine that I think you said that it's so hot that it causes the atoms to evaporate.
Right.
And so how hot does that have to be? I just was shocked that it was able to do that.
Yeah, so for the boron, it starts to evaporate. The temperatures are higher than 1,000 Celsius, but for our work, we heat the boron source to 1,600 Celsius. The silicon, I apologize, I don't know the exact temperature because we don't use a direct heating method. We actually use a highly energetic electron beam, and we point that beam at the silicon so that wherever that beam is hitting, it gets so hot that it evaporates. And that beam is at about 9,000 volts. So it's a lot of energy that we're putting into that silicon to make it evaporate.
What source do you use to have energy?
It's the silicon source is called electron beam evaporator.
Okay.
And for the boron, it's just a thermal evaporation cell. The technical name is Knudsen cell, Knudsen, but that's just named after a person. It's just you put the boron in a ceramic holder, and then you heat that holder to the temperature you want.
Okay. Thank you.
Yep.
I'm curious, what process did you all go through to figure out that you could alter the silicon layer like that to allow the photons to enter into it? Were you part of the team that like researched that? How did you all figure?
No. So one of my colleagues, Michael Hoink, was working with silicon-based detectors, and he was the one who first found that if you do this really highly doped layer right near the surface, you could change the band structure in this way. But there was a lot of work with silicon detectors. I showed that there are traps at that crystal interface and how that can affect that dead layer, the dead layer properties. So there was a lot of work trying to eliminate the dead layer, and they were doing, trying to do doping in the bulk of the material. So having, instead of just where we just look at the last 5 nanometers through the surface, they were looking at a few microns and trying to do doping there. So it was kind of a big deal that Dr. Hoink figured out that if you do this very, very thin, highly doped delta layer or highly doped layer, that it would solve a lot of the problems that people were trying to attack. And that was in the 90s. So I think the first paper came out when I was in 6th grade.
So I have a question. So like how fast paced is it? Like what's a normal day for you? Like how does it go about?
So the work itself of working on a project is a lot slower than you would like. So we started working on this SPARCS CUBESAT. We started writing proposals to get funding to do the work. So the principal investigator, Professor Skolnick, had this idea back in 2015. We wrote a proposal and we got funding a couple of years later. And we are just now getting to the point where we could finish the camera. So that whole process is really slow. But in any given week, I am in the lab about 30% of my time. So doing the growths or getting ready to do a growth or just making sure that machine that I showed is working the way it's supposed to. I spend a lot of my time writing proposals, trying to get funding for the work that we want to do. And I even sometimes will review proposals that other people have written. So I've gotten far enough along in my career that I'm occasionally asked to review other proposals and say whether or not I think it's worth funding. And then I do spend a lot of time in meetings, sadly. So talking about those budgets and schedules and managing things.
How much did it cost for you how much did you guys have to get in order to fund your project?
So I do have a slide about that. I wasn't sure if you guys would be interested, so I didn't want to just dive right in. I'll share my screen again. So for the SPARCS project, the program that we're working on, so these small CubeSats, you can do those pretty cheaply, but we're working on a mission that wants to do science that other people haven't done before. And our cap on that is $10 million. So we can't go over that. But I have a little slide about, sorry, I don't know why I have an animation. Let me see if I can get rid of this. There are a lot of different types of programs for NASA. You start with the large or flagship missions. These are things like Hubble Space Telescope that you might have heard of. And these are what they call civilian scale scientists. So it's of national interest. They are named items on congressional budget. So Congress actually has input as to whether these missions should proceed. And for the whole mission life from start to finish, that can cost several $billions. For smaller missions, these are where you have a scientist or who puts together a team of other scientists who have a specific question or a specific set of questions that they want answered. So as I say here, they have specific objectives. And those can cost anywhere from tens to hundreds of millions of dollars, depending on how big they are. So for the small Explorer, it would be no more than 100 million. For a medium, you could go up, maybe to $400 million. And then there are what they call supporting or research and technology development. So this is like the CubeSat that we talked about, but there are also, you can launch test instruments on suborbital payloads. So this is like something that looks like a weather balloon that goes up into the stratosphere and does some measurements that can't be done from the ground, or even sometimes something that goes on a sounding rocket. And those are between, a few 100,000 to, no more than $10 million. And so sometimes if you just want to do, if you have a technology question, I've gotten proposals awarded where the entire amount of money they gave me was $10,000. I was like, I think I can do this thing. Can I have a little bit of money to do a proof of concept demonstration? And so they said, yeah, we think that might work. Here's $10,000. And then if it works, I can write a proposal to try and get more money to develop the technology.
How did you get into this project? Like, what led you to want to do this?
I was working at JPL right after undergrad. And to work, just like with any job, if you want to do work, you have to, we have to fill out our time card, just like everybody else. And we have to have someone who's willing to pay you to do a specific job. And I was working on a task that was completely different from this, but they didn't have enough money to pay me full time. So we kind of put out some feelers, and I found this group who was working on UV detector technology, and they needed someone. And mind you, I was just out of undergrad when I first started working for this, for my boss. Her name is Shalane Niksad. But she took a chance on me and hired me to work for her about half-time. And it worked out. It was interesting work. So when I was leaving grad school, again, looking for a job, I saw that she had another opening. So I applied, and she hired me back full-time to do this work.
I just kind of had like a general question or two about, so would you say like you said that you were looking for a job after grad school, so were you trying to like, I know that like networking plays a big role in finding jobs like after school, so like, how would you say that like you went about networking, and if you didn't, like, what would you have done?
So I'll say after undergrad, the job that I got after undergrad was fairly serendipitous in that I was doing research in college. I was in the chemistry program at George Washington University, and I was in the ACS, American Chemical Society, accredited path. So they require that I do some research with a professor there. And the professor I was working with knew someone at JPL who was looking for an intern. So he put me in touch with her, and I reached out. We talked about what kind of work I might be doing. I applied for the internship, and I got that internship. And through the course, it was a 10-week internship. And at the end, they said, after you finish your degree, would you like to come back? We could hire you. And this again was where they could hire me about half time. So I did that. It was a pretty sweet gig moving from Washington, D.C. to Los Angeles. I really love it here. And then when I left, I was there for about 5 years, and then I left to go to graduate school. And when it was time to leave graduate school, I had made some contacts through working with my PhD advisor. I applied to postdoctoral positions with a few of them. Like I said, I knew that my old boss from JPL was looking for someone, so I applied for a job with her. I was really keen to move back to Los Angeles. I went to graduate school in Boston, and I wanted to get away from the cold and back to Los Angeles, which is where I really felt comfortable and at home. And JPL is a really great place to work. So yeah, when I started looking for jobs, I talked to contacts that I had made in grad school. So like other professors at other universities, I thought maybe I could work with them. I didn't look at industry too much. I was telling Mr. Sanders before this call started that you can get paid a lot if you want to work in industry in this type of field, but that comes with a lot of stress and a lot of hours, and I wasn't interested in working 80 hours a week. So I think some people have to leave. Thank you very much for coming.
Thank you.
So I mean, I can stay if there's more people who have questions, but
I was going to suggest if anybody
up.
can stay, please, April would more than like that. Keep answering questions as long as she can stay and we can stay.
I do have to go, but thank you so much for answering my questions. It was very, very interesting.
Thank you,
Nice
Emily.
to meet you.
I'm just wondering how like GPS prepared you for all of this, like school and just like the career path.
Oh my gosh. So this may sound silly, but I think one of the most important things that GPS has taught me, one is how to keep a schedule, how to keep to my schedule. Two, how to keep a good lab notebook. I have so many colleagues who don't take good notes, and so when you're trying to figure out what they did, it's really difficult. So yeah, education always is very important, but those time management and record keeping skills, like I said, it may sound silly, but they're extremely important. What do you think about that, Mr. Sanders?
I was very glad for the lab notebook comment. Thank you.
Oh, it was huge. I mean, I see people, I heard of a woman in grad school who, if she made a mistake in her lab notebook, she would white it out. And I can't, never do that, ladies. Just draw a single line through it and move on. So, anything else?
This is just like really cool to me because I'm like looking at the same career path, and I toured George Washington virtually, and that's like the college that I'm looking at. How did like you, and I don't know, how did you end up where you are today? Like what were like all the steps that you took, like major steps?
The major steps. So we can look again at where I went. So like I said, I mean, this is not really actually very useful. But like I said, I was working, I had to work with a professor in undergrad because in the chemistry program, if I wanted that ACS accredited degree, I worked with them. And that included a summer program where I was working in the lab. I think it was about 6 or 8 weeks during the summer where I was working in his lab as well. And at that point, the move to JPL, like I said, was very serendipitous. It was, he knew somebody who was looking for an intern. And looking back, I probably should have been more proactive, but I was lucky that he was looking out for me. So it was, maybe it came down to choosing the right professor to work with because I had a few options. This particular professor was looking at something that just sounded cool when I was 18. He was shooting lasers through flames and trying to figure out what the flame was made of. So I thought that sounded really cool. So that's what I did. And so that's what led to the job at JPL. And then talking, when I got there, you're not limited at JPL by what degree you have. So I had a bachelor's degree in chemistry, but I was working with material science type stuff. I was developing chemical sensors. I was working with this group who was making UV sensors. But it really was a matter of making sure I talked to my supervisor, telling them what kinds of things I was interested in, and making sure that we found opportunities to work on those types of projects. And when it was time to go to grad school, I knew that I wanted, for personal reasons, I moved to Boston. So I looked at graduate schools there. There were just a few that caught my attention. MIT, of course, are always interesting. I looked at UMass Boston, the University of Massachusetts in Boston, because they had what I thought was a very interesting environmental chemistry and policy type program. So I was thinking, if I wanted to move away from the lab and more into doing, national policy type work. But ultimately I ended up at Tufts because when I visited there, I got a really good feeling from the people who worked there. I got to meet with some of the graduate students and some of the professors, and they were all friendly and open. When you go to places like Harvard and MIT, they're friendly, but you quickly learn that the different groups don't really mix with one another. So you may know two people in the same department, but they don't know one another. And I thought that was really strange. I also liked that at Tufts, for the graduate student population, it was almost 50-50 male-female ratio, which is hard to find in chemistry. And then moving back, when I was in grad school, I started thinking about jobs. I just realized that my time at JPL is a really great place to work. So I started looking for opportunities. The JPL website lists job openings, and I reached out to my old boss, and she was looking. I saw that she had been looking, so I applied. They brought me out for another interview because I was going to be doing work that was slightly different than I had done before. But based on my graduate work, it turned out to be a really good fit because all of my graduate work was with surface chemistry type things. So being able to understand how that surface behaves, like the surface of the silicon detector behaves, they really wanted that in a candidate. So it worked out for me. And so I've been with her now with that group now for about 8 years. Slowly getting more and more responsibility, like I said, meaning managerial type tasks. Does that answer your question? Does that help at all?
That was so helpful. Thank you so much.
Yeah.
All right. Thank you. Bye.
Have a good afternoon.